We're in Rosen section 5.1, talking about mathematical induction. Um, we have seen that mathematical induction can be used to prove statements that are equalities, statements that contain inequalities, and mathematical claims in general, as long as they can be stated as a propositional function in n, where n is a positive integer or n begins a sequence of integers that goes up. Um, Here we're going to see another concept. It has the same underlying structure where we'll use induction on a number that increases by 1 to prove a mathematical proposition. And what we want to show is that we're going to consider a checkerboard that is 2 to the n by 2 to the n in size. And then if we remove a square, we can tile the checkerboard using something called a right triomino. And a right triomino is an L-shaped tile which covers 3 squares at a time. Here's an example of one, and of course we can rotate it um, to cover any 3 particular squares if they're available to be covered. All right, and so here's our proposition, our propositional function. Pn is the proposition that every 2 to the n by 2 to the n checkerboard with 1 square removed can be tiled using right triominoes. And then we're going to use induction on n in this size. Well, we'll start with 1, so this will be, so n is strictly positive. And P1 is true because each of the 4 2 by 2 checkerboard, that is 2 to the 1 by 2 to the 1 checkerboards, with 1 square removed can be tiled with a single right triomino. Here's a 2 to the 1 by 2 to the 1 checkerboard, and you can see if we remove any one square, if we remove that square, we can cover it with a triomino. If we remove that square, it's covered with a triomino, remove that square. So we've covered all cases, and it's pretty straightforward to see that the basis case is true. Now we move on to the inductive step, and we must establish the inductive hypothesis. Pk is true for an arbitrary positive k, that is, 2 to the k by 2 to the k checkerboard with any 1 square removed can be tiled with right triominoes. On the next slide, we'll restate the inductive hypothesis in border up there, and then we'll continue with the inductive step. Now let's consider pk plus 1, that is a 2 to the k plus 1 by 2 to the k plus 1 checkerboard with 1 square removed. The way we're going to do this is we're going to split this checkerboard into 4 checkerboards, size 2 to the k by 2 to the k. So here's our 2 to the k plus 1 by 2 to the k plus 1 checkerboard, and I'm splitting it into 4 that are 2 to the k by 2 to the k. And now it doesn't matter which square I remove, I'll just have to remove any one, it's arbitrary, but it must be in one of these 4 smaller checkerboards. So I'll just illustrate it by removing that one. Now what can we say about that lower right checkerboard? Well, according to the inductive hypothesis, that's a 2 to the k by 2 to the k checkerboard with 1 square removed, and by the inductive hypothesis, we can tile that board. How can we tile the other 3 checkerboards? Well, the way we're going to do that is going to remove judiciously 3 tiles near the center of that and be able to use the inductive hypothesis there. So here I've removed 3 more squares from each of the other checkerboards, and by the inductive hypothesis I can now tile these 3 checkerboards. They're 2 to the k by 2 to the k with 1 square removed. And then finally, and I think you can see this now, we will be able to tile this uh, um, these three adjacent removed these three adjacent squares in the center of the um, checkerboard with a single triomino. So uh, since we were able to show that we could tile a 2 to the k plus 1 by 2 to the k plus 1 checkerboard, assuming the inductive hypothesis, then P to the n is proved true for all n greater than or equal to 1.